This map represents the distribution of marine biomass across the entire planet. The varying shades of the ocean are the measurable signature of light interacting with the water column. These hues are the direct result of electromagnetic waves physically colliding with microscopic matter. By isolating the specific wavelengths that exit the water, we can quantify the concentration of organisms deep beneath the surface. Because these organisms pull carbon from the atmosphere to grow, decoding this photon signal allows us to calculate the ocean's role in the global carbon cycle from orbit. Tracing this data requires us to follow the path of a single underwater photon all the way to a satellite sensor array. This mathematical reconstruction is the only way to separate the true state of the ocean from the optical interference created by the atmosphere. Modern marine optics began by overturning a long-held error. Lord Rayleigh, whose work explained the blue color of the sky, assumed the ocean was blue simply because the surface acted as a mirror for the sky. This surface reflection model was challenged by physicist CV Raman during a voyage across the Mediterranean. Raman proved the ocean's blue color originates within the water volume itself. Sunlight penetrates the surface, backscatters off molecules, and returns upward. This shifted oceanography's focus inward, forcing scientists to track how light interacts with subsurface particles. This requirement made human-scale tools like the Forel-Uhl color vials obsolete. Subjective visual matching cannot account for the complex physics of volumetric scattering. Progress in marine biology necessitated a transition from human visual perception to rigorous mathematical radiometry. The foundation of this optical model, before we account for any organic life, is the baseline medium itself, pure H2O. Within this medium, a photon's survival depends on its wavelength. Pure water exhibits preferential absorption. It is highly efficient at absorbing red light, stopping most red photons within the first 50 meters. Blue wavelengths are absorbed less frequently, penetrating up to 200 meters. When surviving blue photons strike water molecules, they undergo backscattering, reversing their vector towards the surface. This balance of red absorption and blue backscattering creates the baseline color. Deviations indicate organic impurities. The water's biological and physical constituents define its inherent optical properties, which are completely independent of weather. Phytoplankton are the most significant biological variable. They use the pigment chlorophyll A to power photosynthesis, capturing solar energy to convert dissolved carbon dioxide into organic matter. This biological process leaves a specific spectral signature. By absorbing blue and red light for photosynthesis, phytoplankton leave behind a distinct green peak in the reflectance spectrum. Dissolved organic matter, or CDOM, absorbs blue light even more aggressively than chlorophyll, shifting the water toward darker hues. Mineral particulates cause broad spectrum scattering, creating bright milky signatures. These three signatures, chlorophyll, organic matter, and minerals, mathematically compete to alter the baseline blue signal of pure water. By isolating these specific IOPs, we can reverse engineer the biological and chemical composition of the seawater. Measuring this from orbit requires scaling the physics up to the macro environment through apparent optical properties. Unlike the inherent properties of the water, apparent optical properties fluctuate based on external factors, like the sun's angle and the clarity of the sky. Remote sensing relies on the ratio between the downwelling irradiance falling on the surface and the water leaving radiance that emerges back out. This ratio is known as remote sensing reflectance. It is the raw data captured by orbital sensors. The mathematical bridge between these macroscopic observations and the microscopic biology is the Radiative Transfer Equation. This equation links the microscopic scattering and absorption of photons to the large-scale light field we observe from a distance. Solving the Radiative Transfer Equation allows us to translate a macroscopic measurement of light back into the biological reality of the ocean. Attempting this measurement from space introduces a massive hurdle. The satellite must look through a thick, dense column of atmosphere to see the water. This atmosphere scatters its own light, called air light, which is significantly brighter than the signal coming from the water. To put this in perspective, the actual radiance exiting clear blue water is a minuscule 2 milliwatts per square centimeter per micrometer steradian. We use atmospheric correction to mathematically strip away this air light, isolating the faint signal that actually originated from the ocean. Once isolated, algorithms analyze the ratio of blue to green reflectance to determine the concentration of biological pigments. Mapping the biological ocean from orbit is essentially a process of aggressively filtering out the atmosphere. This global data map is the final, synthesized output of those physical and biological models. Because we can precisely measure chlorophyll concentration, we can verify the total biomass of phytoplankton across every square kilometer of the ocean. The Radiative Transfer Equation provides the logical link from the scattering of a single photon to the macroscopic biological health of the planet. Tracking these concentrations allows us to monitor the base of the marine food web in real time. By mastering the optical physics of light, we can now track the biological engine that sequesters gigatons of carbon from our